Hello and welcome to the session. I am Dr. Akshay Kumar, and today I'll be discussing with you about an exponent evaluation algorithm, and we'll be discussing about the efficiency of that exponent evaluation algorithm. But what is exponent evaluation? You all know about it. Exponent evaluation is just computing the value of exponent of a particular number. Let's say 2 to the power 13 you want to compute. So that is exponent evaluation, right? But where are this exponent evaluation used? Well, it is used in cryptography, right? While you are trying to solve the polynomials, you would like to do exponent evaluation and so on and so forth. So what is the brute force method? If we say of evaluating exponent, we all know about it. Suppose I want to compute 2 to the power n, okay, or let's say 2 to the power 4. So I simply put it down as 2 multiplied by 2 into 2 into 2. That is 4 times multiplication. So how many times we will be multiplying? Basically 3 times, right? So as far as brute force method is concerned, when we are multiplying when we are trying to evaluate the exponent power 4 of 2, we are just multiplying 2 at least 3 times with each other. And that is going to result into the related exponent value. Now, what is the efficiency of this kind of an algorithm? So if you are talking about an algorithm where you are computing a to the power n, right, that multiplication as brute force method will be represented as n minus 1 multiplications of a, right, with the a itself. And what basically it tantamounts to that ultimately it is the number n. That means the overall efficiency of algorithm is of the order of n, because you are performing n minus 1 multiplication. So that's very simple, but can we do better than that, right? So definitely we can do better than that, and for that we would like to learn about a very important method which we call binary exponentiation. Now, binary exponentiation is a very interesting and intelligent method, and you should learn this so that you can apply this particular method in different situations, right? So what binary exponentiation do? It splits the exponent using the binary representation and do the multiplication. What does it mean? So, for example, if we are trying to compute 4 to the power 14, right? So, the value of n happens to be 14. Now, if I want to represent the power 14, it is going to be represented as binary number. Now, what would be binary 14 as far as the conversion into binary is concerned? That is, binary is 1110, right? Now, using this 1110, this is 14, right? Because 8 plus 4 plus 2, right? 8 plus 4, 12 plus 2, 14, and 0 is just there, right? So, it's total 14, okay? So, you may do exponentiation as how? Let's look into the table. If I say 2 to the power if we are starting from the left, 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, and 2 to the power 3 is 8, right? Now, we need to perform a to the power 14. So, how we are going to do? 4 to the power 1 equals to 4, right? So, that is what we will do at 2 to the power 0th place, right? Then 4 to the power 2 becomes 4 4s are 16, 4 to the power. Now, when we are doing 4, at the 4th places, what we will be doing? We will be multiplying whatever we have already done. That is, we have already obtained 16. So, we will be multiplying that particular 4 to the power 2 with 4 to the power 2. In effect, we will be utilizing the lower terms in order to compute the higher term, right? So this is how we are going to do this multiplication. So it is 16 to the power 2, technically speaking. So we will be getting 256. And then in the next iteration where we are computing 4 to the power 8, right? We are going to basically multiply 4 to the power 4 with 4 to the power 4. So what we are doing, basically, whatever multiple we are getting in the first instance, in the next instance, we are reusing that particular multiple, right? So 1, 2, 4 and 8. So that is the first digit we will be operating, or first multiplication, it's just 4 to the power 1. But when we are doing the second multiplication is 4 square. But the third multiplication is 4 square into 4 square, which becomes 4 to the power 4, right? So the third multiplication becomes, that is 4 to the power 4. And then it will be, next multiplication is going to be 4 to the power 8. If there is any more multiplication, then it will be 4 to the power 16. So like that, you will keep on multiplying towards the higher end side, right? So this is what you would do. But you have not obtained the result so far. What you have obtained is, basically, you have obtained the exponent, that is exponent at 1, exponent at 2, exponent at 4, exponent at 8, and then exponent at 16, exponent at 32, and so on and so forth. So the binary value of your actual exponent, right? So whatever is your actual exponent, in our case it was 1, 1, 1 and 0, right? Or if we go from left, that is right to left, that is 0, 1, 1, 1. So 4 to the power 1, exponent is 0. So what we will take? Just the value 1. Okay. Next, if it is 4 to the power 2, it was 16. And now it contains 1 as far as exponent is concerned. So 1 into 16 is 16. In the next case also, it is, that is what you are getting is 4 to the power 2. Next, 4 to the power 4. Next, 4 to the power 8. And since the first digit was 0, so we will just use 1. So what we are effectively multiplying, 4 to the power, in the last step we will be multiplying only those terms which are appearing in the exponentiation terms, that is 4 to the power 8, 4 to the power 4, 4 to the power 2, and instead of 4 to the power 1, we will be using only 1, because the exponent value at that or the place value of the exponent at that point of time was 0. Alright, so effectively we are multiplying 4 to the power 8 multiplied by 4 to the power 4 multiplied by 4 to the power 2 and multiplied by 4 to the power 0, which is 1. So what we will be effectively getting? We will be getting the value which is 4 to the power 14. And this is how we have done the binary exponentiation. Now, there has to be an algorithm. It is not just that we will be able to do this particular thing without the help of an algorithm. Well, there are two basic techniques which exist for computing this kind of a situation. The computation which we have done is from the right till the left, because that's where we started. That is 4 to the power 1, then 4 to the power 2, then 4 to the power 3, like that, or 4 to the power 4, and then 4 to the power 8. So we went like that, right? So this is right to left binary exponentiation. Now the algorithm for this is very, very simple. Okay, so what is the input to this particular algorithm? The value A on which we are doing the exponentiation, right? The example which we took was, the value of A was 4. Okay, and the binary string of length S, which contains the exponent, okay, and that exponent n as an array, right, as an array consisting of AS. Now obviously, what if we are referring to as a binary exponent, in the last example what we had was 1 1 1 0. So it is going to be 0 1 1 1. That is what AS is. And what is basically our indexing is that A0 is going to contain 0, A to the power 1, A1 contains 1, A2 contains 1, A3 contains 1. So that is how we will be storing the values, right? So S will be contained as from right to left, that is 0, 1, 1 and 1 in the reverse order, right? So what is going to be the final value of the this particular algorithm? The output is going to be a to the power n. So what we start with, we take a variable, let's say x. So we assign a to x, and if a0, like that is the least significant bit, right, which happens to be 0 in our case, right, in this particular exemplar case. So if a0 equals to 1, then result equals to a, else result is 1. That's exactly what we have witnessed when we were discussing the example. So a0 was 1, in our example was 0. Therefore, we took result as 1. Then we will move from, for I is equal to 1 to s minus 1, right? So what was the index x? 0. So a0 happens to be the first, the least significant bit, and thereafter we have to consider a1, that is the next significant bit, the next and so on and so forth. Okay, and what we will be doing every time, we will be, first of all, we'll be squaring the value, right? The value of x. So we started with x equals to a. Now we will be making it a square. In the next iteration, it will become a to the power 4. In the next iteration, it will become a to the power 8. Next iteration, a to the power 16, and so on and so forth, right? However, this multiplication, so squaring is going to take place every time. But if ai equals to 1, only then we will be multiplying it to the result. Otherwise, it is going to be multiplied with 1. That means result multiplied by x, and then you are just returning the result after your for loop is over. Alright, so this is the basic algorithm. Now, example, the same example, that is 4 to the power 14 is repeated over here. N is 14, right? So that is 1, 1, 1, 0, which means a0 is 0, a1 is 1, and a2, a3, both they all are 1. So the value of s is 4. So this binary string will be stored in the reverse order. That is what is very, very important. Okay, and then the initialization of, or the value assignment x equals to a will bring 4 to x. So a0 was 0, so result remains 1, as we have discussed. So the iteration, so the first, when I equals 1, x to the, what we obtain, x becomes 4 to the power 2, that is 4 square, right? And since a1 equals to 1, so result, we will be multiplying this particular value. Then at the case of I equals to 2, x equals to, it becomes 4 to the power 4, right? So a2 is also 1, so result will be 4 to the power 2 into 4 to the power 4 now. And then I equals to 3, here x is 4 to the power 8, because every time the power is, basically we are multiplying 4 to the power 4 with 4 to the power 4. So it becomes 4 to the power 8, right? And the value of a3 is 1, therefore result is 4 square into 4 to the power 4 into 4 to the power 8, which is actually 4 to the power 14. And in fact, when you will be outputting this particular result, it will be the multiplication or the multiplied result. This is just for the sake of showing you that we are shown the result in the case that is 4 to the power 14. But actually, it is going to be the final, the calculated product, which is going to be shown by this particular algorithm. So in a nutshell, this particular algorithm is doing the multiplication. Now, what is the efficiency of this particular algorithm? Now, if we can look into the number of multiplications which are going to be performed by this particular algorithm. Now, if I think in terms of brute force method, since we are doing a to the power 14, there will be 13 multiplication as far as brute force method is concerned. But in this particular algorithm, the 14 is going to be represented in how many binary digits? Just 4, right? Up to 15 you can represent in 4 digits. So you need just 4 digits to represent that particular value. Now, out of those 4 digits, That means you will be multiplying, you will be starting with 1, but till 1 to s minus 1, you will be multiplying x repeatedly. Although you are just doing 4 to the power 2, then 4 to the power 8, 4, then multiplying 4 to the power 4 like that. But your multiplications are just 3 for 4 digit binary number, right? So you are just multiplying x 3 times. And in addition to that, wherever there is 1, right? So assume that 1 is everywhere, okay? Then the number of digits, number of times which are there, you will be multiplying once again. So in effect, you will be multiplying twice, almost twice the number of binary digit. In fact, less than that. So it turns out that your algorithm is going to contain very, very few multiplication. Now let's take another example of this particular situation. Now algorithm remains the same, but now we have done the computation of 4 to the power 17. Okay. Now when we are looking for 4 to the power 17, what that is 1 0 0 0 1 16, okay? So this is 17 in binary. So what is there now? S becomes 5, right? And when x equals to a equals to 4, right? So value of a is equal to 1, so result becomes 4. The else condition, that is the result equals to a, then condition becomes true. Okay, so a0 is 1, so result becomes 4. And the iteration then are like that. You are just multiplying x, doubling x every time. Okay, not doubling, like you are just multiplying x with itself. Okay, so for I is equal to 1, x become 4 square, I is equal to 2, x become 4 to the power 4, I equals to 3, x becomes 4 to the power 4, and for I equals to 4, x become 4 to the power 16. However, the value of a1, a2 and a3 are 0, right? So you are just not doing anything else, just multiplying. Technically we are multiplying it by 1, but as far as algorithm is concerned, algorithm says do nothing, right? So therefore result remains at 4 in all these 3 places. And towards the end, when I equals to 4 is there, what you are doing, you are multiplying with that is, so a4 is 1, so therefore you are multiplying this particular x, the value of x with the result, which was 4. So 4 into 4 to the power 16 becomes 4 to the power 17, which was your final result. Now looking into the complexity of algorithm, as we have discussed, that for computing a to the power 17, the number of multiplication is just 5. The brute force method requires 16 multiplication. And the complexity analysis of this particular algorithm says this algorithm performs either one multiplication or 2 multiplication in each iteration of a for loop. So the total number of multiplications for computing a to the power n will be in the range s minus 1, because we are requiring only s minus 1 multiplication, which is less than the function, the number of multiplication required by this algorithm, and this is less than twice the number of multiplication, because for the first value we are not, like this a0, we are not doing any multiplication. For a0, we are just taking the value as a or 1, depending on the value of a0. If it is 0, we are taking it as 1. If a0 is 1, then we are taking it as the value a, right? Where s is the length of binary string equivalent to the exponent n. So f is the function that represents the number of multiplication in terms of exponent, and the complexity of algorithm, since s is a binary representation of the exponent value n, therefore it is going to be that is of the order log 2n, and n can be represented in binary by using a maximum of s bits only, right? So that is how we are going to represent as n equals to 2 to the power 5, or s becomes order log 2n. So this is the complexity of algorithm. However, there is another way of doing this particular computation, and that computation is from left to right binary exponentiation. Now this is a very interesting situation. From right to left we have done, but now the second algorithm we will be doing from left to right. Okay. Now left to right is basically we will be starting from AS, and the iteration indexes basically are going to be what is, once again you see the binary value, if it is 1110, we will be storing it as 0111 1 in the reverse order, right? Okay. So input to this left to right binary exponentiation is going to be once again A, right, which is the number which we want to do the exponentiation, and the string of length S for exponent n as array AS, and final value is still going to be a to the power n. However, here the process is different. We'll assign a to result first for I equals to s minus 2. So the first, that is the topmost digit, A3 is always going to be 1, right? The topmost digit is always 1 because that is how we are representing A, okay? So that is why we are starting with result equals to A. So for I equals to S minus 2 because the digits, suppose we have 4 digits, then it is 0, 1, 2, 3, right? So S minus 2 in this particular case becomes 2. So 3 already has been taken care of. So we will be starting with the next digit. Okay, so that is how we will be using. So result becomes result into result. Okay, so we will be just multiplying the result first. So if A1 equals to 1, then result will further multiply in the result as A and return the result, and this process continues, and finally we will be returning the result. Let's take an example and that will explain this particular algorithm. So how we are starting with, the value of n is 14, so it is 1, 1, 1, 0. That means A0 is 0, A1 and till A3 is 1. Okay, then we are starting as result equals to 4, right? That is the value of A. Now iteration indexes are 0, 1, 2, 3, and that's what is represented. So when we say I is equal to S minus 2, in this particular case it becomes S is 4, so it becomes 2, right? So that at 2, what we have, first we will double it, okay? So we will multiply 4 into, we will square it, right? 4 into 4, so it becomes 4 square. Since A2 is 1, so we will multiply it by another time A. So this becomes 4 to the power 3 or 4 cube. Now I equals to 1 results, once again what we are doing, once again we need to multiply again. Okay, so result will be multiplied for first iteration, it becomes 4 to the power 6, and since ai equals to 1, it becomes 4 to the power 7, and for I equals to 0th position, when we once again multiply 4 to the power 7 into 4 to the power 7, it becomes 4 to the power 14. Since A0 was 0, we obtain the final result as 4 to the power 14. Suppose this computation can simply be explained as, what we basically are doing is something like this. At index 3, digit is 1. So index becomes 4, right? Result is equals to 4. Exponent so far used is just 1. As we include index 2, digit is 1, result become 4 into 4 into 4 to the power 3. So exponent so far used is 1, 1, which is 3 in technically speaking, the same as this. Next case, we simply we square that particular value and multiply it by 4 because digit is 1. So it becomes 3 into 3 into 4, so 4 to the power 7. Exponent so far is 1, 1, 1, which is 7 itself, right? And in the final case, it is 4 to the power 7 into 4 to the power 7. So final exponent is basically 14, and that's what you get towards the end. This is how this particular algorithm works. Another example of this particular algorithm is with 4 to the power 17, and here S is 5 and the values mostly are 1, so you will keep on multiplying. You start with result equals to 4, and then each iteration you will be multiplying 4 by 4, then 4 square by 4 square, then 4 to the power 4 with 4 to the power 4, and 4 to the power 8 with 4 to the power 8. Towards the end, since A0 is 1, so you will get, right, that is A0 is 1, so you will be multiplying it by 4 and you will get your actual answer. Okay, so complexity of this particular algorithm, either you do left to right or right to left. In both the cases, the number of iterations or the number of multiplications are going to be s minus 1 between s minus 1 and twice of s minus 1. And since the s is being represented by order log 2n, therefore the overall, if you see overall efficiency of this particular algorithm, it is going to be of order log 2n. So what we basically have covered is in this particular session is the exponent evaluation algorithm, which has an efficiency of log 2n. And what you can see that if you are utilizing a brute force algorithm, the efficiency is of order n. And this particular algorithm is giving you order log 2n. Think in terms of, suppose you have to compute 5 to the power 200, right? So in the case of brute force method, you might have to take care of 199 computations. Whereas in this particular case, how many computations in the case of exponent evaluation, you might have to perform maybe 8 or 9 total 18 multiplication or so, which is far less than 199 multiplication. So it leads to very efficient results. So next time onwards, you also try using a binary exponentiation method when you have to do the multiplication in your common way. With this, we end this particular session. Thank you for being with us.